Hello everybody. I just wanted to record the process that I go through to derive an empirical fit equation between a relatively uncharacterized sensor like the red channel on our LED versus a reference sensor. In this case, I'm using a BH1750. It's a medium quality lux sensor, probably not the best, but since we're just demonstrating the principles, this is good enough. The sensor in this case is a red 10 millimeter RGB with no diffuser on it. It's inside the plastic housing we use for our student loggers, and that logger is suspended in a skylight window. So the light is passing through a layer of glass and the logger itself before it reaches both of these sensors. So there's some non-optimal aspects there, and we're also using natural light. And as we'll see from the data itself, that almost always gives you other issues to deal with. But it's not worth worrying too much about the fine details here. It's just the process I wanted to walk through because this is a generalizable approach. I could just as easily be working on a thermistor or a CDS cell. The idea is don't lose sight of the forest for the trees. So let's get to it. This is a data set from yesterday. I haven't had a chance to look at it, so there's probably, as I said, some suboptimal aspects to this. But the first step is always make a copy. Don't work on your raw data. Always save your raw. So this is going to just be trimmed to the data that's relevant. You can see I've got a few little artifacts here from turning on the logger. And if I scroll to the bottom of the file, this is when I collected it, and I was carrying the logger in my hand, and it had various spurious readings. So you always end up with orphans in your data. But for our purposes of a cross calibration, the only data that's relevant is the data where there's enough light that the BH1750 was actually reading. So I'm just going to delete the dark data there. Again, this is our BH1750 column. I'm just going to highlight that, and then we'll scroll down here until we get our first readings. All the nighttime data is just zeros, so we can't really use that for anything. It's worth noticing, though, that the LED sensor works perfectly well during the night. The street light and urban light bleed through is more than enough to get a reading off an LED because it has so much higher sensitivity. Okay, so there's the beginning of our lux data. There's our trim data set. And you can see that I took 2 readings off of the red LED. I'm running the BH1750 here at its fastest setting, which takes a reading at about 5 milliseconds. But even that is long enough for you to get a delta between the start and the finish of that reading. Light changes instantaneously, faster than any sensor. So to deal with that, I bookended the lux reading from our reference with 2 LED channel readings. And again, it's the red channel that I'm using here. And we're just going to draw an average of the LED reading. Okay, so that's G7 plus H7 and divided by 2. And hopefully that will deal with any temporal errors. You always need to think about time quite carefully when you're dealing with light. With temperature sensors, it's not such an issue because it's usually, they have so much thermal inertia that you don't get this issue. But with light, you have to always think about time. So there's our average. And to make a graph of the, just looking at the raw data, I usually scroll to the bottom of my file, select 3 columns, Control-Shift-Home, and then use the Shift key and the down arrow key. And there's my selection. So I've got my timestamp row and 2 data rows. Since I'm just quickly whipping off a graph here, it doesn't matter what that data actually is. I'm just going to set it up here and right-click on one of the lines, change series chart type, and throw that on a second y-axis. Again, this isn't the data I want. I'm just quickly grabbing it here so that I can move these columns. So, oops, there's one of my data series. We'll make that the average LED. It's a red LED, so we'll change that to a red line. And this is logarithmic data, so we need to invert the axis as well. So values in reverse order, logarithmic. And we can change the scale here. So there's 100 as our highest reading. So there's the raw LED readings from the sensor run. It doesn't look too bad. We've obviously got some noise there. And I grab the other column and just drag it over to the Lux column. So there's the readings from our BH1750. And let's fix up the time axis here. One thing about these time axes is I don't like the way it always ends up with these sort of odd digits here. So if you put 0.125 in here, you'll align with even hour marks, and I just find that it makes the data look a bit nicer on the graphs. All right, so there's our raw data, and we can see that this was a day that transitioned. So the overall curve shape's easy to determine, but you can see how gritty this is. And usually this kind of grit is from high level clouds. So we've got light level variation, but it's not strong. And then in the afternoon, we transition to a cloudy day. And so we've got these huge transitions from 10,000 lux up to 50,000 lux. I mean, that's a dramatic light level difference. I also know that because of the system we're dealing with, we have some shadow crossings on the logger. And so the interesting thing about this shadow data is it's not necessarily bad data. It's only bad data if the two sensors are being exposed to different conditions. And we will see some of that in the afternoon because there's a tree near my house that passes shadow lines across the logger. And so some of this data here around 3 o'clock is going to be bad data. Whereas this stuff here, where there's these huge light transitions, this will probably be okay. But either way, because this isn't a perfect blue sky day, we're going to have a lot of grit. And this grit basically produces noise in our residuals. We'll see that in a second. So the next step is to graph the lux versus the LED data opposite each other. And so we'll go down to the bottom again. I usually select up when you've deleted a lot of data. If you select down, you'll get all the empty rows. So selecting up, Control Shift Home, Shift arrow key moves your selection, and insert. And we'll just throw a scatter plot on there. Now I think I have the axes. Yeah, the axes are reversed there. So let's click on our data and switch those around. All right, so now we have lux on the y-axis. That's the independent, which I know a lot of you will not be happy about that, but Excel is what it is, and so that's just the way we have to do it. Now I've looked at a lot of these trend lines, so I can kind of get a sense of what kind of data this is. But when you're just initially looking at a raw sensor, you don't know if you've got an exponential or a power law. So one of the nice ways to quickly do a check on that is to format the axes logarithmically and take a look if that transforms your data into a straight line. So instead of actually doing the linearization, we can just change the axes. And so this is a semi-log plot. And if this had produced a straight line by me simply changing the dependent variable to logarithmic, it would have indicated that we had an exponential relationship. It didn't, so we don't have an exponential. But if I then go to the dependent and independent and make them both log, the fact that we've translated our data into a straight line, this is the signature of a power law. So it can be difficult to see the difference between an exponential decay and a power law. And so this is just a nice little trick to remember that if the log-log plot shows you a straight line, that's what you've got. You got a power law. So I'll just undo those. And we will add a trend line. Okay, and you can see it defaults to linear, but we know it's power from our little log-log trick. Display equation on chart, r squared, and I usually change the format of the line a little bit here. I'll just make it a black solid line so that we can see it on our data. And the reason I like to do that, if we zoom in here, is that now that the trend line is actually a black line, we can see if it wanders. Sometimes when you have a problem with your fit equation, you can see that the line will wander in and out of the data plots. And so it's just nice to be able to do a visual check. Reformat our label. Again, the LED sensors can give you up to 8 digits, so I'm just going to make the constants being displayed have the same number of digits as the actual data. It's probably in excess here, and you can click right into this label and take away some of those excess digits. So I'm not even sure the R squared is meaningful past 4 digits anyway. Right click, go to home, change the size of that so that we can see what we're working with. Okay, so there's our power law trend line constants. And we're going to just copy those out and drop them into some cells here so that we can do the manual calculation for our fit. So this is our A constant for the power law. This is our B constant here. It's a little tricky grabbing these, but so this is our calculated lux. Okay, and our equation here is going to be A times x raised to the power of b, J2 times our x in this case is the raw LED reading, hat for power, and J4. And there's our calculated lux. I'm just going to format that so that it gets rid of some of the excess decimal places. And instead of scrolling, you can just click on this little green square at the bottom and it will fill down. And it'll fill down wherever there's data in the adjacent column. So that just saves you from doing a lot of scrolling there. Okay, so there's our calculated lux. Next step is to take a look at some error metrics. So we want our error calculation, so our residual. And I usually do it with the sensor reading that I'm calculating with minus the accepted reference. So in this case, that's the BH1750, but this is probably backwards. I always get this wrong. This is the way that makes intuitive sense to me because the sign of the absolute error indicates whether the calculated reading is above or below the reference, but I think this is backwards. Anyway, doesn't matter. Once you see the graph, it's pretty intuitive. So J7 minus F7, the BH1750 reading. So there's our absolute error, and again, just copy it down with the green square. And here's our relative percent error, percent RE, where we take the absolute error that we've just calculated. So that's K7 divided by, again, the accepted reference, the BH1750, that's F7, and then times 100 to get the percentage. All right, so there's our percent relative error. And even though this graph has a reasonably high R squared, you know, with nonlinear systems, the R squared is, you really can't use it. You have to take a look at your error, your absolute and your relative error before you have any sense of whether the system is behaving or not. So I just copied that graph. I'll delete the trend line and then grab my axes. Now I usually graph error in a system like this against time rather than against the reference because it makes more sense to me to be able to take a look at the data in conjunction with the raw. So let's just do a little cleanup on the axis here, get rid of the decimals. And the time axis is confused again, so time 30, and we set our major to an even divisor, and there we are. So now we have column indicators in the same places, and I find it very helpful to be able to line up my error with the raw data so I can see the trends. So this is our absolute error, or our residuals. And now let's look at our relative percent error. Maintaining the same formatting. Just gonna pull this over here. So these dots are a little fat. Let's format the data series just to make things a bit smaller so I can change to a built-in marker. 3, no line. All right, so there's our error, our residuals, and our percent relative error. And this is really the information that lets you get into an understanding of whether your system is working. We've got some artifacts in this data, and you can see that the ends go way out. And these wings at the ends, these are an artifact of how fast I was reading the BH1750. To reduce temporal errors, I was reading it as fast as possible, but that reduces the sensitivity, and so you get errors in very low lux levels. In fact, I think this system, really doesn't behave well until you're up at around 200 lux. In fact, we can make that determination. I'm just going to move these out of the way here. Okay, so let's just click on the graph here. 526. So what light level were we at 526? That appears to be where the error sort of got back under control. So 526 is down here. So I'm just going to sort of arbitrarily say that I don't trust the lux values below this point, and that's about 100 lux, and that sort of matches my experience with these sensors. And if we go to the other end, I'll bet you again at 1822. We scroll down to 1822, and what do we see for the lux level? Yeah, again, we're sort of in the 100 lux level. So, I mean, just arbitrarily, I'm going to say we're not going to use data below 100 lux for this comparison, simply because I don't trust, I don't really trust the BH sensor readings from that point. So let's expand this graph a little bit. And we've got some other artifacts in our percent error, and they're much harder to spot. Like the residual, the raw residuals, it's easy to spot the error in the center of the day, but it's much harder to spot these at the ends of the day because the absolute value is so small. But as a relative source of error, they obviously jump out. This is the shadow line crossing the logger right here, and there will be an inverted equivalent spike at the end of the day, and that shows up down here on the plot. So we basically have two physical artifacts that produce bad data in our system. So I'm going to make another copy of our graph of our data, and I'm going to call this one Prune Outliers. You want to be gentle here. You really need to know about, the conditions in which the run was made before you can do this safely. But let's just see if we can get a better fit by getting rid of the data that we know is bad. So I'm going to delete all the data under 100 lux, and I'm working on a copy. So my original data is safe. I'll do the same thing down here at the end. Okay, and then we will take a look at this. These residuals. So it looks like our shadow crossing spike starts at 6:58, so about 7 o'clock, and it looks like it's passed fully at around 7:42. So 7 to 7:42, we've got bad data because of the shadow line crossing. All right, so I'm just going to highlight that and take this data out of our set. All right, and that's going to create a gap. There we are. So that shadow line crossing spike has been removed, and I'm going to go do the same thing here for the opposite spike in the evening. And this noise right here, this is a result of a tree. We have a tree where the shadows of the branches of the tree sort of wave back and forth and create some interference on the data. So we actually have some more bad data to delete here. So I'm just going to sort of determine where those tree branch shadows started. looks like at about 315 and going all the way to the other side of that window shadow spike, 630. So 1630, 15 to 1630, we have questionable data for our fit. So I'm just going to select that down, 1630. Again, we're removing data from two physical interferences here. All right. Okay, so I'm going to call the rest of this more or less valid data. When you're doing pruning like this of outliers, one thing to be aware of is that the trend line does not update. So we have to delete the trend line and reapply it to get new constants. Okay, it's a one-shot deal. Again, we bump this up to 8 digits. So we have, just as a rule of thumb, I use the same number of digits as the sensor produces as raw data. I don't know if that's exactly correct or not, but all right. And if we just compare these two, this is an empirical fit. So all of the provisos, about not using an empirical fit outside of the range of the calibration data set apply. But let's take a look. What we have here now is 18 million is our A constant, where we had 21 before. Not so much of a change to the exponent, 0.978 versus 0.999. So I would, because I know the physical system, I would call these constants more accurate. Probably won't have too much effect. Let's just put them in place. If we're lucky, we will have reduced the error somewhat. Okay, so those are the constants from a fit to the pruned data set. Let's just bring the relative error from the trimmed data over and put it beside. So this is trimmed, and this is pruned. And let's change this to same numbers on the axis. And you can see that after we've gotten rid of the outlier data, interestingly, we even have more structure in the residuals and the percent error. So this tells me something. If I've removed data that I know is bad, I've ended up with more structure in these graphs, it means that this structure is not probably a result of a bad fit equation. Normally, when you do an empirical calibration and you look at the residuals and you see a lot of structure, it means you've got a bad equation. You need more terms. This is a very different physical system. The light that's hitting one of our sensors is being filtered through bulb lenses, and then it's hitting a reflector. There's internal reflections inside of the LED epoxy. And so, instead of going further, for example, we could do the squares of the absolute error and then the sum of the squares, and we could run the solver on that. As soon as I start to see systems that don't do what I expect, which is I've pruned away outliers and I've actually got more structure in the errors, that tells me that there's physical aspects of the system that need attention. I'm not gonna improve anything by running the solver on this, because this isn't a fit problem in terms of the math. It's a fit problem in terms of the physical system. So that's where we go from here. You can have high R-squared values in a complicated system and still have, errors that are sort of functionally not useful in terms of using your sensors. So let's go from here and take a look at the physical system and see if we can bring the LED closer to the cosine curve response that you see from the BH1750.